Hello, what I'd like to do today is talk about the Earth coordinate system. We're going to talk about latitude, longitude, and also how longitude is used to determine time in the universal time zones. First thing I want you to do is to actually imagine this planet not as being a stationary thing with this program shows, but also a revolving and rotating object. Right now I want to talk about the rotation, and remember that the Earth rotates counterclockwise, rotates this direction. The equator is always found by this Nile delta, Nile cut into South America, and also the line that goes under here, which you can see is located right there, on that line that goes underneath Africa. And the first thing I want to know is when you get this, actually I can probably show you a couple of these things. Here you got to be careful when you look at the rotating Earth. This is actually a Wikipedia site, and it's got the Earth rotating the wrong direction. It has it rotating this way. As you can watch North America move, moving the wrong way. Here's one that actually has it going the right direction. This one actually shows you the day-night line as well, where you can actually move the AM line, daylight, sun up, and then move halfway around the planet. Remember, half of the planet's lit up at any one time. But anyway, when we start talking about this rotating Earth, there are three places that actually can be used as a reference point. And remember, reference points are any point that pretty much is stationary. You don't want to use a dog as a reference point. You want to use a stop sign. You don't want to use a mailman as a reference point. You want to use a mailbox. But anyway, the way we take a look at it is way up here we get the North Pole, and celestially we call that the pole of the north. And then down here we get the South Pole, which is the pole south. And then equidistant from that, if we can actually go in and erase this line, that doesn't look like that. Need to make that ink flow a little better. And I'm going to make this eraser a little bigger. If we went in and we actually found points that were halfway distant between the North Pole and the South Pole, we would end up with drawing like dots. There's one that's halfway in between, except where there's one that's halfway in between, and there's one that's halfway in between, and there's one that's halfway in between, halfway in between, halfway in between, halfway in between. And we can see these going halfway in between, and then all you have to do is go in and make another line, and we call this thing the equator. So those are the three things we can use, and from this we can come up with a coordinate system. Between the North Pole and the South Pole we draw parallel lines that go all the way across. These guys are called latitude. They are these lines that look like this. They're parallel to the equator. The equator does actually create the planet, or divide the planet into two hemispheres. It divides it up into a northern and a southern hemisphere, two half spheres. We don't have a line that goes north and south, but these things just keep getting smaller and smaller and smaller and smaller. The equator is this one right here. So anything above it is actually called plus. And this one's actually showing the North and South Pole. The South Pole is actually up here and the North Pole is really there. This makes a north end of a magnet with the side that's not the South Pole. Remember, south and south repel each other. Makes the north point up and this south point down. But anyway, we call these pluses. This is the northern hemisphere. And we call these minuses for the southern hemisphere, because the northern hemisphere came up with this system. Here's another example where we actually have the line that's 15 degrees, because remember 90 degrees is 45-degree angle. Should be drawing a right angle shape there, not a circle. But that's a 90-degree angle. So we have 15 and 30 and 45 and 60 and 75 and 90. Again, these are the pluses. And then we have the same thing. We have 15, these are the north, so these are degrees north. These are going to be degrees south. And we got 15 and 30 and 45 and 60 and 75 and 90 degrees south. And these are negative numbers. plus numbers. If you actually want to use north and south, you don't have to worry about positive and negative, but if you just want to say 60 degrees plus, everybody knows that's above the equator. 60 degrees minus, that's below the equator. Now the next line we get for longitude is completely man-made, and what we did is we, back in the 1600s, 17th century, came up with this idea that we wanted to actually figure out time. We didn't have any trouble at all going north and south because we could use Polaris or the sun to actually figure out where we are north and south, but we had some difficulty figuring out east and west. So what they did is they actually said, okay, let's make a meridian, which is, remember that line that goes between north and south, crosses your zenith, goes through Polaris. Let's make a meridian that we're going to use as our reference point. And we literally could have put it everywhere, anywhere we wanted to. Good place for it would be through Washington, D.C. We could have made it through Paris. Could have made it through Ecuador. We could have made it through Panama City. We could have made it through Philadelphia. Could have made it through Los Angeles. But what they did is they made it through Greenwich, England, which is right about there. It's a suburb of London. So what they did is they actually said, okay, this line is going to be what is called the prime meridian. It's going to be the zero line. It's this line right here going through Greenwich, England. And then you have every 15 degrees, you got 15, 30, 45, 60. These are west, so now we actually have a western hemisphere and an eastern hemisphere. These are the minuses, just like, and these are the pluses, just like these are the pluses, and these were the minuses. And this time we actually go 180 degrees because we can go 180 degrees this side all the way around, and we can go 180 degrees this side all the way around. So we now have an eastern and a western hemisphere, as well as a northern and a southern hemisphere, and from that we can find any point on the planet. Okay, here's one that's got it all the way through. It's got the North Pole, has the South Pole, has the equator, has the prime meridian going through there, has parallel lines of latitude. They're always the same distance apart. These are called meridians. They're the same distance apart degree-wise as latitude down here on the equator, but if you notice, they get closer and closer and closer and closer and closer together. If you were Santa Claus, probably should make him red. If you were Santa Claus, if you were Santa Claus, you'd actually be anywhere on the planet you wanted. Okay, so this one was actually made from Peoria. It talks about Greenwich, England. If you take a look, Greenwich, England is 50, looks like maybe 51 degrees north, because we give latitude first, and it is by 0 degrees latitude, so or longitude. So we have to write longitude because we can't write either north or south or east or west when the number is 0. Just like you're on the equator, you can't write 0 degrees north or 0 degrees south. So here is Forest Park High School. This is where I teach, and we're located at about 38 degrees, really close to 40 north, and this is the, if you actually look at it, 15, 30, 45, 60, actually it does have it 75, right around 77 degrees west. So that's the way we can find it. So if you want to find Peoria, Peoria looks like it's about 41 degrees north, and it looks like it's almost right on 90, so maybe 89 degrees west. If you want to find that location right there, looks like it's about 8 degrees north by 7.5, maybe 7 degrees west. Doesn't really show you the eastern hemisphere all that well, but we could actually say that point right there. This point would actually be about 7.5 degrees. And the way you'd actually write that probably is 7 degrees. Each degree is divided up into 60 minutes, so 7.5 is 30 minutes. And then you could say 0, 0, but probably more than that, seconds, degrees north. And then it would actually be, I messed that one up. Let me take that off, because I gave you the wrong one first. If we wanted to do this one for real, if I can get another 3, don't need that. So if we go back and we look at that line again, it is 1023 degrees north by 7 degrees 30 minutes divided up into 60 seconds, and this would be east. Okay, so you can find any point on there. Go down and here is what's called the Mercator map. Mercator maps actually take all the lines of latitude, which are parallel, shows them parallel, just like they would on the globe, but now they actually take all the lines of longitude and make them parallel. And what that does is makes this line that goes through the Nile River Valley, the equator, makes this point exactly the way it's supposed to. And the farther you go up, if you take a look at these boxes are square. They start getting rectangular. And all that means is that they're actually stretching things. They stretch them east-west, they stretch them north and south, so that makes Greenland look the size of North America when it really should actually be about this size. Makes North America larger than it should be. Florida is not as exaggerated as Maine, which is not as exaggerated as Alaska. So this is a map, very convenient, shows north at the top, south at the bottom, west over on this side, east on this side. So if you're going in a particular direction, you know exactly where you're going, even if you're going in between, but it is exaggerated. But you can find any location you want. There we are again. Here is the prime meridian, which is actually prime meridian, which is 0 degrees. Here's the equator, which is 0 degrees, and we have 1, 2, 3, 4, 5, 6 lines going up. There's probably 7, so these are probably 15 degrees. So if you actually look at it, we go 15, 30, there's 45, so we get right around 38 degrees north by, and we have 15, 30, 45, 60, there's 75, like 77 degrees west. And you can find the location of any place you want. But again, this is a coordinate system. You need to figure out how far up and down, and to do that you need lines that go side to side. Those are called latitude. And you need to figure out how far you go east or west, and to do that you need lines that go up and down. You call those longitude lines. We always do latitude first and longitude second. Okay, here is Forest Park High School. Here is the latitude, 38.61111 degrees, and negative 77, because remember on the western hemisphere, northern hemisphere is positive, western hemisphere is negative. You can do away with the positive negative if you just write north and south, east and west. But there is my classroom, and this is where we're sitting. The people who are watching this video, who are supposed to be watching this video, that's where you would sit. Mr. Payne's classroom. It's right across the hall right there. Okay, now we're going to talk about longitude and time. If you take a look at it, we take the prime meridian, which is this line right there, and we take a look at the Earth, which revolves, rotates, again, this direction, counterclockwise, and we rotate 24 hours. If we take 360 degrees, and, degrees, let me get rid of that. We take 360 degrees and we divide it by 24 hours in a day. We get 15 degrees per hour. So there's 1 hour of rotation. If we're located right here, we would end up being right here 1 hour later. And there's 2 hours, and 3 hours, and 4 hours, and 5 hours, and 1/4 of the way through the planet, we'd be spinning over in this direction. If we made the sun right here, excuse me, the point that actually is facing right at the sun, which in this case would be this way, this would be the 12 noon position. And then we make the sun move a little bit towards the west, which is this side, and then we make it move more towards the west, and then by the time we get over here, we may actually see the sun setting. This time of the year sets right around 8 o'clock. It was more like 9 o'clock a while back, and fairly soon it'll be over here around 4:30 standard time, 5:30 daylight savings time. But we can make the sun set, and then we can go all the way across to here, which is the 12 midnight time. So that's the way we figure out time zones. Taking a look at this picture, if this one we have 90 degrees east, that's 12 noon, then we'd have 90 degrees west, which is midnight. The times are exactly opposite each other. 3 o'clock this side is 3 o'clock that side, except this is 3 o'clock in the afternoon. The daylight side, this is 3 o'clock in the morning, and 3 hours later the sun comes up. And here are the time zones. They look like this. If you look at the United States, we actually have 4 time zones in the contiguous. We actually have 5 and 6 if we throw in these 2 states. But the contiguous states, the ones that touch each other, we have the Eastern time, we have Central time, we have Mountain time, and we have Pacific time. And if you take a look at it, here is Greenwich England. This is Greenwich Mean Time. This is time zone 0. This one over here is time zone 1. This is also time zone 1, but this is the plus side because this is 1 hour after, because the Earth goes this way, sun goes that way. So 12 noon is here, won't be 12 noon for 1 more hour, so this is the negative side. So that makes me, who lives in the Eastern time zone, that makes me in time zone -5. Because here's -2, -3, -4, -5. That makes Paris, France, which is in this white time zone, +1. So it's in time zone +1. So anytime it is whenever time it is in Greenwich, England, you add 1 hour. We subtract 5. So there are 24 time zones, and you can see them down here. There are a couple funky ones. There are some countries that don't actually want to be in the same time zone as the countries that are around them. So this one we actually have to add a half an hour. So if this one is 5, this country is 5:30. This one is 5:45. So the ones that actually have pluses, and I'm not sure why they do that, but they do that. Well, why wouldn't this just be the time zone that it's in? They actually adjust it by half an hour. Time zones are not straight up and down. They should be, but you notice they zig and zag for countries because this country wants to be in the same time zone. This is what's called the International Dateline. Doesn't say it anywhere, so I'm going to write IDL. And if you actually say it's, let's say it's 7 o'clock in the actually that would be evening, 7 o'clock in the evening here, there's 6 o'clock, there's 5 o'clock, there's 4 o'clock, there's 3 o'clock, 2 o'clock, 1 o'clock, and then this one is the 12 midnight space. This one, it actually becomes the day after. So this one is, let's say today is actually, what day is today? Today's Sunday. So this is Sunday here on this side, and it's Sunday all the way over till you get to here, and then at 1 o'clock this is the Monday side. And it's Monday all the way to here. So here's the Sunday area, half the planet, and there's the Monday, half the planet. When it becomes 12 midnight here, the entire planet can be on the same day. But 1 second later, this side becomes the next day. What makes it really cool, if you can actually get into an airplane, and let's say your birthday is November 17th, You'd be sharing birthdays with me. Let's say you're on this plane on November 17th. Let me restate that, because that's not going to work. So I want to undo the 17th. Let's say you're on this side of the International Dateline and you celebrate your birthday here. It's the 16th on this side. If you could cross this line right at midnight, this side becomes the 17th, and you can celebrate your birthday for 2 days. If you go the other way, you can actually miss your birthday, because if it's the 16th and you wait until 12 midnight on this line, then this date over here becomes the 18th, and you weren't even on the planet on the 17th. This is a man-made system of time zones. We had to make a man-made system of creating the fact that you can't just keep going back. If I keep going back in time, I can make it yesterday. And if I go this way, I can make it tomorrow. So I can go over tomorrow and watch all the sports. I can come back here and make bets on them because it's yesterday. And then when it becomes tomorrow here, I know what the scores are going to be. So this is time zones. What we do is we add hours. Going this way. And we add days crossing this line. And you can see why this wants to zig and zag. We don't want to actually have this part of the Soviet Union or Russia now tomorrow when this side is today, even though they're on the same time zone. So it does zig and zag for island nations. Notice that the time zones can zig and zag. International Dateline can zig and zag. And this one actually becomes the same time on 2 different days. Really weird. Okay, the last thing is Polaris. If you can actually watch Polaris or any constellation, this is the celestial sphere, so this is the point of rotation. If you watch the Big Dipper in the spring, it's really high in the sky, probably 70 degrees up, almost close to your zenith. If you look at it 3 months later in the summer, it's dialed over here. This would be like at 12 o'clock. This one puts it over here at like 9 o'clock. And if you watch it 3 months later, which is going to be really close to now when school starts, it's going to be here at 6 o'clock, really low, close to the horizon. And remember, here in Virginia, we have that problem with trees. So it's possible that your location, you won't even be able to see this because of the trees or the bushes or houses. But it is over here really close to the horizon, and then 3 months later it moves over this way for the winter, and then 3 months later we're back into spring. So it moves that direction. And then what we're going to do probably today in class or next day in class is we're going to make what's called an astrolabe. And I'm going to need you guys to bring in a weight. Usually this means a washer. Or a nut, like a nut and bolt and washer. We're going to use that, and then we're going to take a piece of string. We're going to take cardboard, because you're also going to need a cereal box. We're going to make a half protractor. We're going to tape a straw to the top of it, and we're going to use it to sight things in our room. And I'm going to want you guys to figure out the height. And what we can use this for is to figure out Polaris. And if you can figure out the height of Polaris, you know your that's crazy. Latitude. And from here in Virginia, we should be able to sight Polaris really close to about 39, 38 degrees. And I may even have a project where you take it home and you can find some things, but I haven't done that in a few years. I probably will not do that today or this year. Thank you much. Bye.